Right, it's time to roll out the big boys of integration. This is integration by parts. So the product rule is something that we've used in differentiation, and we're going to use the fact that if we integrate, it cancels out a differentiation, and we're going to integrate all of this statement. So we're going to say, well, if the product rule is true, then it must also be true that if we integrate both sides, then we still have the same thing. And then we use the fact that integrations and differentiations cancel out. So the left-hand side is saying the integral of the differential of uv, which is just uv. And we are going to split the integral on the right-hand side into a sum of two separate integrals, which is fine. We did that last year as well. And then we're going to do one last rearrangement here. We're going to subtract the v du dx from the left-hand side, and that's going to give us this statement, the integration by parts rule. Now I'm going to leave that up at the top of the screen. We're going to run through a few examples of how this works, and we're going to talk about like when would you pick things to be different parts of it. But the idea is that integration by parts can be used to integrate anything which is two things multiplied together. One of them is u and one of them is dv dx, and we can rearrange them to get the statement on the right. So let's use this y equals x e to the x as our example. We're going to say that u is equal to x, and we're going to say that dv dx is equal to e to the power of x, because those are the two things that are being multiplied together. And if we want to fill in the right-hand side here, we need to find a value for v, and we need to find a value for du by dx. So differentiating x is just 1, and integrating e to the x is just e to the x. We can then take those things and we can sub them into the formula that we've got there. So it should be uv, so that's going to be x e to the x if we want to integrate y. Take away the integral of v du. So v is e to the x and du is 1. Now if we tidy that up a little bit, we wouldn't write e to the x times 1, we'd just write e to the x. And then what we've got to do to finish this off is integrate again. We've got to integrate that e to the x. So we'll have x e to the x, take away, well, the integral of e to the x is e to the x, which is helpful. It's an indefinite integral, so we should put a plus c on at the end of all this. And that's it. That's our integration by parts used. X e to the x goes to x e to the x minus e to the x plus c as an integral. And the important question then becomes, well, we've got two things in this statement. We've got u and dv, and we do different things with them. So we need to decide which is which, because some way around will make it dead easy, some way around will make it dead hard. So we've got a choice here of like 3x and sine x, which is going to be u and which is going to be dv. And so what we have is essentially the late rule, which we use to decide which is going to be the thing we set u equal to. I've had some people call this the u-late rule, just to remember that it's what's setting u equal to, so you could do that as well. And these all stand for fairly large areas of maths. L stands for logs, A stands for algebra, T stands for trig, and E stands for exponents or exponentials. And we go through that tier list, and the first thing we come to is what we're going to set u equal to. So we look at this question, and we say, well, are there any logarithms in it? There are not. So we go to the next thing. Is there any algebra in it? By algebra, we mean like polynomials. And there is. There's 3x. That's the first thing we've run into. So we'll say that u is equal to 3x. And whatever the other thing is, that's our dv dx. That's our sine x. After that, it's dead easy. We just run through the process of differentiating u, of integrating dv dx, so it's going to go up to minus cos, and then taking those values and putting them into the formula. So the integral of y is going to equal uv, so minus 3x cos x, minus the integral of v du, so that's going to be minus the integral of minus cos x times 3. And then tidy this up a little bit. We have got a minus minus here, so we would change this to the integral of plus the integral of 3 cos x. Then we'd actually do that integral, which would go up to 3 sine x, and don't forget the plus c. So yeah, that late rule is crucial for doing this efficiently and effectively. look at another example here. We've got algebra and we've got logarithms. So we are going to use the logarithms as our value of u. We are going to say that u is equal to ln of x squared, and dv by dx is equal to 5x squared. We are going to differentiate u, and remember the shortcut for a logarithm is to put the function on the bottom of the log and its differential on top. And that can actually be simplified. So rather than 2x over x squared, we could make that 2 over x. And then dv dx, integrate that. So increase the power, divide by the new power, so we'll have 5/3 x cubed. And once we've got those, plug them into the formula. So uv, which should be 5/3 x cubed ln of x squared, take away the integral of v du, which is 5/3 x cubed times 2 over x. Now that's a bit complicated, so we want to simplify that a little bit. So we will times the 5/3 by the 2, so we'll have 10/3 overall, and we'll got x cubed divided by x, so that's 10/3 x squared. So there we go. We can then integrate the 10/3 x squared, so we'll go to 5/3 x cubed ln x squared, take away, divide by 3, 10/9, increase the power, x cubed plus c. Cool, let's keep going. So these look pretty routine at this stage, so let's go for it. We've got some algebra and we've got some trig, so the algebra is going to be our u, that's 3x squared, and our dv dx is going to be cos 2x. You need to use a little bit of reverse chain rule when you're integrating that. That'll go up to a half sine 2x. We did that 2 weeks ago with f of ax plus b. And differentiate this is going to go to 6x. So let's write that out, and we'll end up with the integral of y is equal to uv, so it's equal to 3 over 2 x squared sine 2x, minus the integral of v du, which is, so a half times 6x, that'll give us 3x sine 2x. And here we can see where there might be a little bit of an issue, because this thing here does not have an easy integral. It's actually going to require another integration by parts. You could call this a second order integration by parts or a two-step integration by parts, but you can be given them, you can run into them. So what I would think would be sensible would be to just work out what I've put in the green box there, just work out that integral now. But we go straight into another integration by parts with it. We've got, again, algebra and trig. So u is equal to 3x, and dv dx is equal to sine 2x. Integrate that, we get minus a half cos 2x. Differentiate u, and we get ourselves 3. And so we can tell that that green box integrates to uv, so minus 3 over 2 x cos 2x minus the integral of v du, so minus 3 over 2, I guess. Yeah, again. Cos 2x. We've got a minus minus there, which is going to become a plus. And then we need to integrate that. So that's going to be minus 3 over 2x cos 2x plus, and then, so we're going to half, so it's going to go up to 3/4, and cos is going to go up to sine 2x. So we've done that, and that is going to have to be substituted into there. So we can finally go to our final answer, which is that the integral of y, as we defined at the start, will be 3 over 2 x squared sine 2x. And then we're taking away this integral, so that's going to change these signs. So this one's going to become a plus, this one's going to become a minus. So it'll be plus 3 over 2x cos 2x minus 3/4 sine 2x. Yeah? So not any more complicated per se, and don't forget the plus c. But that's a two-stepper. We started with an x squared, and it takes 2 steps for that to differentiate away to nothing, essentially. So 2 more of these to show you. One of them is a little bit of a party trick, which is how do you integrate ln x? And the way you integrate ln x is by integration by parts, by treating it as ln x times 1. In other words, that is a logarithm times some algebra will still define 1 as a polynomial. So in this case, we go, okay, so u is equal to, the logarithm is equal to ln x, dv is equal to 1, and we'll differentiate. Ln x goes to 1 over x, and dv integrates up to x. Then we can sub them into our formula. So uv would be x ln x, so this is the integral of y we're finding. So uv, take away the integral of v du. Now v is x, but du is 1 over x, so we end up with x over x there. So that helps a lot, because the x and x cancel out and say, well, we're finding the integral of 1, which is going to give you x log x minus x plus c. So yeah, it doesn't look like it's an integration by parts question, but is a very clever little trick, that one. And then for the last one, don't forget to look at the formula book for particularly the trig integrals. There's a big long list of those that you are expected to, not to know, but to be able to apply by looking them up. And this is an example of one. And we're also doing a definite integral. This question has algebra and it has trig in it, so our u is going to be the algebra, and our dv is going to be the trig. If we differentiate x, we obviously just get 1. If we integrate the dv, sec squared integrates to tan x. That's one of the common results that you've got inside your formula book. So we put them into the formula, and we say that this is equal to uv, so it's equal to x tan x minus the integral of v du, minus the integral of 1 tan x, so just tan x. But then we need to integrate tan x, and luckily tan x is given in the formula book, so we'll just use that. So this is equal to the integral of x, or is equal to x tan x, take away ln of sec x. Normally we'd say plus c at this stage, but this is a definite integral, so we're just going to substitute pi over 4 and 0 into it. Let's do that, and let's try and keep this exact. So we'll sub in pi over 4 first. That will give us pi over 4 times tan of pi over 4. And remember, any trig in an integration question means you're going to be using radians, not degrees. Take away ln of sec of pi over 4. And then we also need to substitute 0 into it as well. So let's do that. That will give us 0 tan 0 minus ln of sec 0. Now you could at this stage type that all into your calculator, but let's do a little bit more if we can. This is going to be pi over 4 times 1, because that's what tan of pi over 4 is. Take away ln of sec of pi over 4. No, that's 1 over cos pi over 4. So if cos pi over 4 is, I think it's 1 over root 2, then sec of pi over 4 is just root 2. So yeah, so this is log of root 2. And then we're going to subtract 0 tan 0, which is 0. Take away ln of sec 0. Sec 0 is 1, because cos 0 is 1. And ln of 1 is 0. So those are both going to be essentially equal to 0. So overall, in exact form, we've got pi over 4 minus ln of root 2. So, integration by parts, give it a go.